All right, so we're starting chapter 4 today. And so with chapter 4 and chapter 5, we're getting into the stuff that is the most chemistry like of really anything that we're going to talk about this semester. And so chapter 4 is titled The Chemical Forms of Matter. We've talked a little bit about some of the stuff in here, but what we're going to get into primarily is we're going to get into a lot more deep information about chemistry and kind of what holds molecules together and why they form chemical reactions in first place. And then in chapter 5, which is going to be our last big chemistry unit, we'll talk more about how chemical reactions take place and what kinds of chemical reactions there are. But we're going to start today with a review of something that we talked about in chapter 2, that is elements and compounds. And so you should recall from chapter 2 that we can break down matter into two basic categories: the pure substances, which are uniform in their composition, so they have a fixed ratio of one element to another, or they are a pure element themselves, and they are completely separate from other materials. And then we have mixtures. Mixtures kind of are everything else: physical combinations of multiple substances together. And so between these two categories, the pure substances and the mixtures, we are talking about all forms of matter in these two ideas. Again, this should be review for us because this is what we kind of started to look at in the beginnings of chapter 2. Now, when it comes to pure substances, we understand that there are two different types of pure substances. There's the pure substance that is a compound. Compounds are chemical combinations of elements. But in a fixed ratio of one element to the other. And so what we mean by that is, if I'm looking at water, water is always going to have a fixed ratio of hydrogen and oxygen, and that ratio is 2 to 1. If I change that ratio from 2 to 1 to 1 to 1, I change the very nature of the compound itself. And changing the very nature of the compound changes its physical and chemical properties. Because they are made of multiple substances, we can break them down into simpler substances. This is a process that usually involves either the use of heat, light, or electricity. So I can take a compound like calcium carbonate, heat it up real good, and carbon dioxide will find its way out of the carbonate and leave behind a white solid calcium oxide compound as a result. I can expose hydrogen peroxide to light and it will decompose into water and oxygen. I can shock water with electricity and it'll turn into the hydrogen and oxygen that it was made of out in the first place. So compounds can be broken apart into simpler substances. It's just a matter of, usually we have to do some form of extraordinary means to do it. Elements, on the other hand, because they are one type of atom, they cannot be broken down into simpler substances. Just can't happen. To break an atom down into its components would require something more like on the lines of a nuclear reaction, which is more than just ordinary means. We're talking about extraordinary means to do that, breaking apart the very nucleus of the substance as opposed to just transforming and rearranging atoms with each other. When it comes to atoms, there are 118 different types of atoms that we call the periodic table of elements. And that periodic table of elements is arranged in a number of different ways that we're going to talk about here later on today. And so one of the things that I'm going to give you is a periodic table for you to write on, manipulate, do whatever you want to. Now keep this periodic table, because when it comes time for exams, and so the exam that you're going to take on Monday is kind of an exception to this. You're really not going to need a periodic table for it. But for future exams where the periodic table is going to be relevant and useful, you'll be able to use this periodic table on your exam. So whatever notes you take on it are usable notes. Now on that periodic table, there are 118 known elements. Each of those elements is given a specific name as well as an elemental symbol. That symbol kind of represents that element in chemical equations. But despite this, only 10 elements are actually responsible for 99% of the Earth's mass in terms of the Earth's crust. If I go into the ground, despite the fact that there are 118 possibilities of elements that I could find there, I'm going to find 10 of them 99% of the time. The other 108 elements are really present in trace amounts, or they're present in other parts of the Earth. When it comes to the periodic table, we can divide that table into basically three groups. There are the metals, the nonmetals, and the metalloids. When it comes to being a metal, obviously we know just observationally what a metal looks like. But here are some common properties associated with metals. We know that metals are good conductors. They conduct heat, they conduct electricity. We know that they are usually solid. In fact, all metals are solid with the exception of mercury. Mercury, number 80, Hg, is the only liquidous non-metal substance. Or excuse me, the only liquidous metal substance. So since most of these are solids, we know that they're going to generally melt at high temperatures, and they're going to boil at even higher temperatures still. Metals are dense. They're heavy. They tend to possess high densities. They are generally malleable. For malleable, meaning that it's flexible in terms of if I hit it with a hammer, it'll start to spread out and thin out into thin sheets. We take advantage of that quite often. We look at things like aluminum, which we can sell in these big, long rolls where the aluminum's been spread out real thin and then rolled on top of itself for easy transport. And then to get what we need, we pull out the length of aluminum and we can cut it and do whatever we want to it. We can also describe metals as being ductile. That's an ability to be drawn into thin wires. This is why we often will use metals in terms of electrical wiring. We know that they conduct electricity well. We know that we can get them very thin. Thinness has a whole lot to do with resistance. The thinner the wire is, the less resistance it'll have, the more readily it'll conduct electricity without getting really hot in the process. Metals are known to have a brilliant luster. Luster is just another way of saying shiny. And as I mentioned before, none of these metals are going to be gaseous at room temperature. Almost all of them are solid. Mercury is a liquid. And virtually none of them, with the exception of mercury, really even vaporize all that easily. Mercury, because it is in the liquid phase, it does exhibit a small vapor pressure. It does slightly evaporate, but not considerably. We can contrast this by looking at nonmetals. Nonmetals are more or less the opposite. They melt and boil at relatively low temperatures. So for the most part, they are gases, solids, and liquids. The ones that are solids tend to melt pretty easily. So when we think about solids of nonmetals, we're thinking about things like phosphorus, sulfur, which generally speaking, melt really easily. Doesn't take a whole lot of heating to do it. We can melt either of those using a laboratory burner. Whereas we really can't melt any of the metals that we've been talking about in the same way. Nonmetals generally are not shiny. They do not have a luster. They are far less dense than metals are. If they conduct electricity, if they conduct heat, they do so very weakly. Generally speaking, they are either in the solid phase, which describes elements like boron, carbon, silicon, phosphorus, sulfur. Arsenic, or in the gas phase, helium, argon, neon, nitrogen, oxygen, fluorine, chlorine, so on. There is one liquid and it is bromine. Bromine, Br, is known to be in the liquid phase. as its elemental state. So it, like Mercury, are kind of the oddballs of the group. Almost all of them follow a particular trend. And then bromine doesn't. Mercury doesn't. So that's metals and nonmetals. What about metalloids? Well, metalloids kind of fit in the middle. So I mentioned on the previous slide about boron and silicon and arsenic. Those are technically considered metalloids. They technically have properties of both. Now, to be completely honest with you, most of their properties are more non-metallic than metallic, which is why I put them on the first list. But there are some aspects of them that are metallic in nature, at least in some part. So for example, silicon. Silicon, when it is in its pure form, is actually not a half bad conductor of electricity. It's not great. It's certainly not like a metal, but it's not bad. It becomes even better if we pair it with something like phosphorus and make what is called a semiconductor, where the extra electron in phosphorus can jump over to the silicon and allow electricity to flow that way. Silicon also has a little bit of a shininess to it, which again, kind of puts it in that middle ground. But as far as its other properties are concerned, it's solid phase, but brittle. So it doesn't have the flexibility to be pounded into sheets or drawn into wires. You smack it, it breaks. Again, conductivity properties, certainly better than expected, but not terribly great at all. Unless we either get it really, really pure, or we pair it up with something like phosphorus and create a semiconductor. So now that we've talked a little bit about elements, let's talk about some of the changes that those elements can undergo. We know that any substance is going to be held together by certain internal links, chemical bonds. If it's not held together by chemical bonds, we know that at the very least it's being held together by something to keep it in the solid phase or the liquid phase. If it's in the gas phase, there's really not anything holding it together because, as we talked about with gases, those molecules are super far apart anyway. So what is the difference between a chemical change and a physical change then? Because in both cases, we're talking about the change in the way that the substance is put together. The difference between them is right here. In a physical change, we are going to see the redistribution of energy. We are going to see some sort of energy change. We are going to see some change in the way that the substance is interacting with itself, but we're not going to see a change in the substance itself. Its composition is going to be exactly the same afterwards. So the most common of these would be phase changes. I take ice, I melt it and turn it into water. Internally, the things that were holding that solid together and keeping it in a rigid, solid state are changing. The structure is being relaxed, energy is being added, the molecules are separating a little bit further apart from each other. There is a change going on. But compositionally, every single one of those molecules is still H2O. From a compositional standpoint, it hasn't changed a bit. Other kinds of physical changes are, simple ones. I take a piece of paper and I rip it in half. It's a physical change. I have changed the form of this paper. But compositionally, all the molecules that are in this paper are exactly the same as they were before. Chemical changes, on the other hand, require the breaking of chemical bonds. And when we break chemical bonds, we are going to change the identity of the substance itself. So the substance isn't going to look the same as it once was. It's going to be transformed in some kind of way. Now, the most common examples of those are things like combustion, where we've got a flammable substance and we expose it to oxygen, and that flammable substance interacts with the oxygen and creates new compounds, usually carbon dioxide and water, sometimes other oxygenated compounds as well, depending upon what was in the original substance. Or corrosion reactions. We have something that interacts with an acid. The acid eats away at the substance, let's say the metal, and we end up getting hydrogen gas and some sort of solution of metal and the acid solution left over. We've changed the physical form. Chemical bonds were broken, new chemical bonds of different kinds were made. The net result is we have something different from what we started with. With physical and chemical changes, often come physical and chemical properties. And again, the difference between the two has to do with how we identify them. Physical properties can be done and observed without changing the chemical identity of the substance. So I can go up to an ice cube, touch it, and go, oh, that's cold. That's a physical property. I've done nothing to change its chemical identity. I can make other kinds of physical observations without doing anything other than just looking around. This carpet is orange. That chair is black. This room is large. That door is closed. None of those kinds of observations require me to change anything. In order for a chemical observation to be made, in order to observe a chemical property, we need to be observing a chemical reaction. So these are the things that happen when a substance is undergoing a chemical reaction. This substance burns and it gives off a smell that stinks. This substance corrodes and the metal turns orange in the process. The copper oxidizes and it turns green. Those are chemical observations. So notice sometimes there's a little bit of crossover between properties. I used color in both cases, but the difference was how I used the color, what the color was being describing. If I just make an observation about an object without any context of a chemical change, that's a physical property. But if I'm making some sort of observation while the chemical reaction is taking place, that's a chemical property. Now, one other thing about chemical properties, the absence of a property is also relevant to us often. Think back to what we were talking about last chapter, flammability. Something being classified as not flammable is an important chemical property to notice as well. A lack of reactivity is an important property to note. From physical and chemical properties, these are the observations that we can use to help distinguish substances from each other. So let's just take a look at a couple of substances and how we can separate them from each other in terms of chemical versus physical. So oxygen, for example. From a physical standpoint, you are sitting in oxygen right now. You know it to be odorless. You know it to be colorless. You know that it does not conduct heat or electricity particularly well. If you were to measure it, you'd find that it has a density of 1.43 grams per liter, and that it becomes a liquid at -297 Fahrenheit. So that liquid would classify as a cryogen when it happens. From a chemical property standpoint, we know that it combines with many different substances to form a variety of different compounds. When it does so, we call that chemical process oxidation because of the reaction of oxygen with those things. Let's look at the bottom one, hydrogen chloride, which is a compound. Hydrogen chloride is a gas. It is strong smelling and colorless. Its density is 1.20 grams per milliliter. It is extremely soluble in water. When it dissolves in water, it forms the compound hydrochloric acid. That's actually how most of us know hydrogen chloride is in its acid form rather than its gas form. But if you have a high enough concentration of hydrochloric acid, you actually have the occasion to smell it. That vapor that you get is the hydrochloride gas, and that's actually what burns your nose when you do it. What do we know about it? Well, from a chemical standpoint, it reacts with many, many different kinds of minerals. Dig stuff up out of the ground, and you usually will find an oxygenated compound of some kind, and hydrochloric acid will react very well with it. When it does, it'll form water-soluble products, usually salts of some kind. And if we are interested in the minerality itself, we can use special processes to actually extract the metals out of that for our own purposes. Hydrogen chloride also reacts with ammonia to make ammonium chloride, which is a starter for a fertilizer. It's actually one of the ways that we can get nitrogen into soil. All right, so now we're getting into the atom itself. Now, by definition, an atom is the smallest particle of any element. So if I break down any of those substances on the periodic table and get them down to a single unit, that unit would be the atom. Now, inside of that atom, we have protons, neutrons, and electrons. Those three are known as subatomic particles. And each one of them has a particular job when it comes to the atom. The electrons themselves are negatively charged, and they're going to be responsible for the majority of the reactivity, in fact, all of the reactivity of a given element. When we look at that periodic table and we identify the substances that are reactive versus the ones that are not reactive, it's going to come down to what the electrons are doing in those elements. In the protons, we are going to find positively charged particles. Those positively charged particles are responsible for the atom's identification. The difference between any two elements on the periodic table is all about how many protons are in its nucleus. And then finally, neutrons are neutral particles. We also find them in the nucleus. Their primary responsibility is nuclear stability. We'll get more into that in chapter 16 when we talk about isotopes and the stability of the nucleus. But each one of these subatomic particles has its job. The electron is what determines how reactive the element is. The proton determines what the element is. And the neutron determines whether or not that particular nucleus is stable. Why do we need the neutrons? Well, we know that opposite charges attract, right? So the protons and the electrons are attracted to each other. But what about the protons to themselves? Well, if opposite charges attract, like charges would repel. So the job of the neutron basically is to keep those protons far enough apart from each other, really, that they don't just fly apart. They're there as spacing. And the bigger the element gets, we'll find the more neutrons it's going to have because it's going to need more of that spacing to keep that nucleus together and to keep it stable. And eventually we're going to hit a point where even neutrons can't keep it stable. That's where we get into radioactivity. That's what chapter 16 is all about. So about the atoms, we know that the protons and the neutrons are inside of that nucleus. The nucleus represents that dense middle part of the atom. The electrons themselves reside in this area around the nucleus. In general, we call this the electron cloud. Within that electron cloud, there are specific places, think of them almost like houses, for those electrons to reside in. We call those atomic orbitals. So within this larger electron cloud, there are smaller regions that actually house the electrons that are called atomic orbitals. So let's end today talking about some key definitions and getting into how we identify and how we label atoms. And then that'll kick us off for Wednesday when we talk about the periodic table and some other features. So we're getting into talking about atoms. Now, to describe a given atom, we need some information. One of those pieces of information is the atomic number. The atomic number, which is sometimes represented by the capital letter Z, simply tells us the number of protons in the nucleus. Again, the atomic number is basically the identification of the atom. So if you look at the periodic table on the wall, the numbers in the top right corner, which are blue, tell us the atomic number. On the periodic tables that I gave you is the number at the top of each one of those boxes. So for example, oxygen O is number 8. Oxygen has 8 protons in its nucleus. That's what sets oxygen apart from the other elements. Mass number, on the other hand, is a way of telling us how many particles are in the nucleus. So mass number, which is often abbreviated as capital A, tells us the number of protons plus the number of neutrons. And so if I took those two numbers and subtracted them from each other, I could determine the number of neutrons that were in that nucleus. Isotopes are atoms of the same element that have different mass numbers. So when it comes to atomic theory, we generally say that atoms of the same kind are identical. But that's with one really important kind of proviso, caveat. And that is this. We know that isotopes exist. We know that for a given element, there may be several different isotopes that are present. How do we tell them apart? Well, we usually identify an isotope by its mass number. So we would do things like this, talk about, okay, copper 63 versus copper 65. In both of those cases, we're talking about copper, which has an atomic number of 29. The difference between the two is that this one has a mass number of 63, this one has a mass number of 65. So if we did our subtraction, we would find that this one has 34 neutrons, this one has 36 neutrons. That's where they're different from each other. And those differences usually play out in a number of key ways. Like this one is more abundant than this one. This one's more stable than this one is. in terms of chemical property, pretty much indistinguishable from each other. You wouldn't know the difference. But in terms of their nuclear properties, that's where we might see slight differences between them. And that leads us to this last one, atomic mass. Now, the atomic mass is the relative mass of an atom, and we can even be more fine with this. The relative mass of an isotope compared to the carbon-12 isotope. Carbon-12 isotope has 6 protons, 6 neutrons, and a mass of exactly 12. Every other mass for every other isotope that we know of is measured relative to that mass right there. So what we do is just a direct comparison. This isotope weighs this much. This isotope that we're comparing it against weighs 3 times as much. Well, that would mean that this isotope weighs 36 and this one weighs 12. So we've defined mass based upon this idea. Now, on the periodic tables that I gave you, the number at the bottom represents the atomic mass for a given element. That mass on that table is an average of all of the different isotopes that exist for that given element, weighted to their abundances. So the more abundant an isotope is, the more of an influence it has on the atomic mass. So again, if we consider copper 63, which has an atomic mass of right around 63, it's like 62.9 something. And compare that to copper 65, which has a relative mass of 64.9 something. If I simply just took the average of those two, I get 64, give or take a little bit. But I look at the periodic table, value is 63.5. Why is it shaded toward this one? Because there's more of this one. This isotope is more abundant, copper 63. As a result of its higher abundance, the mass, the average mass of all copper is shaded more in that direction. And so you can look at the periodic table and get a pretty good idea of which isotopes are favored relative to other ones based upon those masses. So you look at something like nitrogen. Nitrogen has a mass of almost exactly 14. Nitrogen 14 is its most common isotope. You look at something like fluorine. Mass is almost 19. Same deal. Most common isotope is fluorine 19. That doesn't mean that there aren't other isotopes that exist, just that that one is the most common and it's very, very, very abundant compared to the other ones. And that is where we will stop for today. So on Wednesday, we will get into kind of summarizing all of that information into one nice little packet. And then we'll get into talking about ions and the periodic table. Have a great afternoon.